Alright, hey guys, welcome back to another Micromouse meeting. Today we have a very special guest. In the chat, his username is JJJ93, but he's also our old Micromouse lead, Joe. And today he's come to give a little presentation on the A-star algorithm. And he's going to be comparing it to, I believe, Dijkstra's and also the flood fill algorithm we're using. So, fun stuff. Okay.
Was that my cue?
Yes, that was your cue.
Oh, all right. Hey guys. Thanks for having me. My name is, like Kay said, my name is Joe. I was a former Micromouse lead here. I think it was, I guess 2 years now. I graduated in May 2019, double major computer science and math. I was in IEEE for 4 years at Rutgers. I did Micromouse for 3 of them, so hopefully I have an idea of what I'm talking about. We'll kind of get into a little bit more of that. All right, should I share my screen then?
Yeah, but I will switch scenes to your screen as well.
All right, you guys are gonna have to bear with me because I'm still kind of new to Discord. But I think you should be seeing something. Everyone see a PowerPoint?
Yeah, we see it.
Yes.
Okay. All right, so as Kay said, we're going to be discussing A-star today. Quite a nice algorithm. I guess just kind of before we get too far into this, what year are you guys, and what majors? Just I kind of want to know how much detail I should go in for some of these things.
I'm a freshman in computer engineering, but I'm thinking next semester I'm going to switch into computer science. But
Okay.
I'm a sophomore computer engineer with a minor in CS.
So have you guys taken I guess in the computer science, it's like data structures. I think software or computer engineering, they have PM2 and all that.
I haven't taken those yet, but I'm gonna next semester, I think.
Okay, so some of this you might hear there, but I guess I'll take it a little bit slow. If at any point you guys have any questions or I say something that doesn't seem quite right, just please go ahead, stop me. Ask away any questions that you have. So I guess we'll get into a little bit of background about A-star, and kind of the whole point of it is to find the shortest path is on a graph. So a graph is typically considered, well, I guess I can skip ahead a bit. This would be an example of a graph. Typically you have you see A, B, C, D, all the letters are what we call nodes, or sometimes people say vertices. Essentially you want to think of this as your Micromouse grid, where your cells would be nodes. So A would be your starting node 0, 0. B would be 1, 0. C would be 0, 1. Just kind of states and positions the robot can be. And you see the lines connecting them. Those are called edges. And in this case, the numbers on those lines, on those edges, are what we call weights. So essentially, from A to B, that kind of marks a connection from A to B, and that 3 means that there's a cost of 3 moving from A to B. So maybe you can think about it it's 3 meters away, and from A to C is 1 meter away. But generally, when we're talking about graphs, would kind of mean something like this. But you could think of it as you're doing a Micromouse, you have a 2D array.
Joe, are you showing a diagram right now?
Yes, can you not see it?
No.
Oh.
I think you have to. Are you sharing your entire screen? Or are you just
I am sharing the PowerPoint. Okay. I went into presentation on the PowerPoint.
Okay. When you in Discord.
Oh, I see what you guys are seeing.
Yeah. So, what we were seeing was just the title slide that entire time.
Oh. So you guys got to bear with me. So I go to share my screen. Change windows?
Yeah.
Screens. Entire, there we go.
Yeah. Okay. Yeah. And now we can see the diagram you were drawing, or yeah.
So you guys can see a full screen PowerPoint presentation with the title being example.
Yeah. Now we can.
Okay. So I guess I'll go through that again. When people usually talk about graphs, this is the kind of structure they're referring to. So you have like the circles A, B, C, D. Those are nodes, or sometimes people say vertices, and the lines connecting them are called edges. The edges mark like a connection between the nodes. So like like if you're at A, you can move to B, and if you're at A, you can move to C, either one. And the numbers on the edges for like the weights, which is kind of like the cost associated with transitioning between those two. So like going from A to B have a cost of 3. You can think of it like being 3 meters away. A to C, cost of 1. You think maybe going like 1 meter away. Like I said, a lot of times you can think of it as this structure, or you could think of it as like a grid in Micromouse, like A being your starting cell at 0, 0. You can move to B, which is at 1, 0. C would be 0, 1. That kind of structure. So it's essentially what a graph is. And kind of the whole purpose, the whole question we're trying to solve here is how to find the shortest path on a graph. And there's only really 2 preconditions you need to for your graph to run this algorithm. The first one being as a finite graph, so it can't go on forever. And the second one is that those weights can't be negative. There's other algorithms out there. If you had negative weights, I think Bellman-Ford would do that. But that's not really an issue with Micromouse, so we're not going to get into that. And kind of beyond that, we want to also find the shortest path, but we also want to find an efficient way of finding that path. Because you can kind of build a path and look at all the different nodes on the graph. But there's some maybe on the complete opposite side where the goal is that you really don't care about looking at, because that's not where the path is going to be typically. And kind of some different terms you see kind of thrown around when you look into A-star. These people talking about tree search versus graph search. I don't really want to get into this too much. We're just kind of stick with graph search. And there's some specific graphs, the way that they're structured, that they're referred to as trees. And that's typically like referring to the structure of the graph. In this case, when we talk about tree search and graph search, we're not referring to that. We're just referring to if we keep something called a closed list, which is essentially a list of nodes we've already visited. So a common point of confusion there. We're just going to be referring to graph search. So kind of going forward, we're going to have this concept of a closed list. You guys are seeing like a background title slide there, right?
Yes, we are.
Okay. So kind of before we get into A-star, there's one algorithm that's very important to understanding A-star. That's Dijkstra's algorithm. I think a lot of times they kind of go over this. You often see in data structures. I think even algorithms that may go into it. It's some of the math classes you take if you take linear optimization or graph theory, probably. You will also touch on this.
Yeah, linear optimization.
So you probably end up seeing this again.
Oh, I'm sorry. Linear optimization, they actually do go into DFS and BFS. I was not expecting that when the professor first brought up the slides.
Yeah, this comes up quite a bit. So if this is the first time you're seeing this, you'll likely see it again. But Dijkstra's algorithm is kind of the fundamental concept behind A-star. A-star kind of builds on top of it. So we're just going to kind of take a minute to review. This is like the pseudocode for it. Essentially, you have a starting state, a starting node, or like the starting cell on your maze, which is like 0, 0. And when we talk about there's like G of S, G is the cost to get from the start to whatever node you're talking about. So at the start, clearly, the cost to get from the start node to itself is 0 because we don't have to move at all. And then also kind of going through this, if we're going to be building a path, we want to keep in mind what our parent node was. Right, because that's that way when we're at the end, when we reach the goal, we can kind of trace that back, build that path back up. Also, very important to the idea of Dijkstra's algorithm is this concept called the fringe. Essentially, you want to think this as a list, kind of like that closed list, where the closed list was the set of nodes we've already visited. The fringe is the list of nodes we are going to be considering next. And we'll get into a little bit more detail about how that is kind of structured, because depending on how you implement it is really how you make the algorithm very efficient. And since those are the list of the nodes we're considering next, we want to insert our start node in there to kind of kick everything off. And we want to order it. Essentially, the fringe is going to be ordered by the cost of the nodes. Like, so you want to think about it as like the least expensive node will always be in the front of that list. So we insert the node with that cost. And then you see the closed list is empty because we haven't visited anything. And then while there's something in the fringe, while there's something we can look at, we're going to take that node out. If it's the goal, then job done. We found the path. We found the solution. If it's not the goal, we're going to add it to the closed list because we've already visited. And for each of the children of that node, so example, if we pulled A out, the children of A would be B and C, because we can reach B and C from A, like directly. Like we could reach D as well, but we'd have to go through another node. We're talking about like just the direct children of A. We're going to check if one of those children, just considering one of them, one at a time, if it's in the closed list, we're going to ignore it. So going forward, we're going to assume it's not in the closed list. And if it's not in the fringe, if we haven't seen it before, we're going to give it a cost of infinity. And we're going to set its parent to basically empty. It doesn't have a parent yet. And then we're going to check if this cost, so the cost to get to its parent plus the cost of transitioning to it, is less than that cost. So as you can see, if it's not in the fringe, then we would see that the cost of the parent plus the cost of transitioning would be less than infinity, right? Because it also could be that we've seen it before and we have to update it. Then we're going to set the cost. So we're going to set the cost to get to the child equal to the cost to get to the parent plus the cost of making that transition to the child. And then we're going to set the parent of that node to the one we just came from. And then lastly, if it's something we've already seen in the fringe, we want to remove it because we just found a better way to get to it. Right? Because otherwise right here, right, this would have been greater than or equal to. So we want to insert with the new cost. I know that might not have been the best explanation. Does anyone have any questions with this?
Any questions, guys?
I don't have any.
Okay.
We kind of went over Dijkstra. I mean, I took data structure, so it's not.
Okay. And then
Okay.
you took data structures, with some other people here
What's
haven't.
up?
Some other people haven't taken data structures yet.
Oh.
Yeah.
Didn't you also? Never mind. My bad.
No. I only said why we're not going to be using data structures. I never actually covered what data structures was
yeah.
like.
So is everyone good with this so far?
Yeah, I'm good.
All right. So we're gonna go through or I guess we will go through an example, but I kind of wanted to talk a little bit more about that fringe data structure, or I guess list. Kind of the typical way it's implemented is the use of a heap. And essentially the way a heap is, it's implemented as an array, but conceptually it's kind of stored as a tree. And what makes this special is you kind of do a little bit of work maintaining a structure with it every time you insert and every time you take out of the heap. And kind of doing a little bit of work each time, you're able to get very efficient kind of removals with it. I'm not going to get too much into this. I know a lot of you are using C++, and you can get a heap implementation with the priority queue class defined in the header queue for C++. I think it's been there since C++ 98, so whatever version you're using, you should be able to get a decent implementation of the fringe. And kind of we're just going to run through an example just to, I guess, get a better feel of this. So we have this graph that I've kind of been pointing to initially. And we're going to start at A. A is going to be our starting node, and H is going to be our goal. So we're going to start, like in the algorithm, we take our start, we put it into the fringe. So from here, the fringe is going to be all the blue nodes, and everything in the closed list is going to be yellow. And typically, things in the closed list we refer to as expanded. So the closed list would be the list of expanded nodes. So from A, we look at its successors. We look at the children nodes, which are B and C. So we're going to insert them into the fringe. And you can see B has a cost. So that's like the G value. G of B would be 3, and G of C would be 1, because it took us three I guess units to get to B and 1 unit to get to C. And then from here, we're going to take, so this is like the next cycle in our loop. We're going to take the minimum value from the fringe, which would be node C. So we're going to expand that, put it in the closed list. And now we can see the new nodes we haven't seen before and add them to the fringe with a cost of 2 for D and 6 for E. And we're going to kind of keep repeating this process, taking the least node out of the fringe each time and kind of adding its children, the new nodes we discover at each point. All right, so we see G now. We can get there from A to C to D to G, the value of 10. But we're going to pick B because it was the least expensive node in the fringe. So we're going to expand B. Now we see F, the cost of 4. F is still the least expensive node now. So we're going to pick that. And now, see, before the G, to get to node G, it was a cost of 10. But now we found a more efficient way and a shorter path to get to G through nodes B and F. So at this point, we had to go back in the fringe and kind of update the value we had associated with G. And now, at this point, G is the least expensive node in the fringe, so we're able to expand that. And we can see our goal, but at this point, it's still not the least expensive node in the fringe. So we pick E, which is the least expensive. And we found we had H again, but this time it was not a more efficient way to get there. The previous way we found H was still the best way to do it. And now since there's only 1 node left in the fringe, we pick that. It happens to be our goal node, and we found our path, the cost of 7. Will I clear everyone? Is there any questions on that? I'll take that as a no.
I think.
Nope.
Oh, does someone have a question?
No, I was saying I
Did
don't
say
have.
something wrong. Oh, you don't? Okay.
Yeah, I think everyone's good.
All right. So kind of at this point, we kind of ask ourselves, can we do any better than this? Dijkstra's algorithm, it's not really directed very well. If you go on Wikipedia and look up Dijkstra's, it actually gives a really good example. You can kind of see how it just picks nodes that are the closest to the center, or the closest from the starting node. So it just kind of, I guess, like radiates out like a ripple, right? It'd be a really nice way to direct it if we could. It's like in this picture, you see the start node is all the way over here on this end on the left side, and the goal node is all the way up here on the right side, and pretty much the whole path sticks to the top. Yet Dijkstra is expanded all the way down to the bottom. So the purple here are the nodes that were expanded. So when the algorithm ended, all those nodes were in the closed list at one point or another, while the yellow path is the shortest path that Dijkstra's calculated. But since we know where the goal node is when we start, at least sometimes, certainly for Micromouse we do, we want to see if we can kind of change the numbers a bit so that when we pick nodes from the fringe, we're kind of favoring the nodes that we think will get us closer to the goal. And that's what brings us to A star. And if you'll notice, this is almost identical to Dijkstra's algorithm. The only difference being, in addition to the G, or our cost function, we also have a heuristic function, H. And basically the heuristic function is a fancy way of saying a guess. So the way you want to think about it is you had your G function, which is the cost to get from the start to a node. And you want to think of H as estimating how much is left from that node to the goal. And there's a couple different properties that heuristic function has to satisfy, which we'll go over in a minute. It's kind of the same thing. So since A star is just kind of an improvement on Dijkstra's, you kind of still need the same properties of the graph, right? It needs to be finite. You can't have negative weights. And those two properties of the heuristic you need, it needs to be both, it needs to be admissible, certainly, which just means it never overestimates. So if you're, if you're at a node in the graph and in reality it will take 10 steps to get to the goal, your heuristic function ideally would tell you 10, but it'd be fine if it told you 8 or 4 or 1 even. It just can't tell you 11 or 15 or 20. And the second property we need is we need the heuristic to be consistent, since we're doing graph search. If we were doing tree search, we wouldn't need this. However, typically when you're doing graph search, you would need a consistent heuristic as well. And a lot of times people say the consistent heuristic satisfies the triangle inequality. And to me, just seeing the picture has helped more than just seeing the inequality. So if you want to think about it from one node, the heuristic value at one node should always be less than or equal to the cost of getting to any one of its children plus the heuristic at that child. Right? Does that make sense? Anyone any questions about that? Before we see any examples of what a heuristic function would be?
You guys good on how the heuristic part of A star works, or
like why we want one, like why it's desirable to have a heuristic? All right. I heard a ding.
Oh, I was gonna say, yeah, I'm good to move on. Like, if the others are, yeah.
All right. Also, I realize I've kind of neglected to mention kind of the trade-offs versus graph search and tree search. Kind of having that closed list and maintaining that, when you have large problems with a lot of nodes in a large search space, it becomes very inefficient and kind of impractical to have all those nodes in memory at a given time. So it's oftentimes like a performance versus memory trade-off, which is a kind of common theme you see in a lot of these algorithms. So tree search, it doesn't need that extra memory, but you're going to run some extra kind of calculation.
yeah, in data structures, you guys will learn more about space efficiency versus time complexity.
Yes, and on that, I am not going to go into time complexity in any of this. wasn't planning on proving anything. So either take my word for it or you look it up on your own. But most of this, saying that most of this, I believe, is right.
Yeah.
But please correct me if I'm wrong. Anyone who knows better, please. So now that we kind of talked about kind of those properties that heuristic needs to satisfy. Oh, also I should mention here, a consistent heuristic is always admissible, but an admissible heuristic may not be consistent. So kind of consistency applies admissibility, but admissibility does not imply consistency. That being said, most heuristic functions that are admissible are also consistent. And typically you're not really going to have to kind of go out of your way to find one of those functions anyway, as we could see several examples of them on this slide. It's kind of like those three go-to functions that at least I've typically seen. So first one being the Manhattan distance, so your delta x plus delta y, which you could see on the is the blue path there. The Chebyshev distance, which is kind of like the diagonal distance, which is the yellow line there. And the Euclidean distance, everyone knows that, kind of the distance, straight line distance on a plane.
Wouldn't Manhattan distance have the same value with the
Oh, okay. Yeah, I know.
Chebyshev?
I know why you're asking that question, Dan. Joe, I actually did cover Manhattan distance and Euclidean distance before, but I haven't went into as much depth with Chebyshev distance.
Okay. So I guess I'll explain that a little bit more then. So the Chebyshev distance, you see there, it's the maximum of your deltas. So if it's maximum of your delta x and delta y. So you can see in the example, the delta x would be 11 and the delta y would be 7. So in this case, the Chebyshev distance is 11 delta x. And you can see the kind of that yellow, if you would kind of like collapse that onto the, I guess that would be the x-axis. You can see that it lines up with, that bottom, the x distance. Or does that make sense? Anyone have any questions?
I think I'm good.
All right.
That makes sense.
Also kind of that first bullet point, it's kind of important how you choose your heuristic. You have to consider how your robot moves. So like in this example, say like typically Micromouse is a 4-directional kind of movements, move up, down, and left and right. And we have to remember that the heuristic has to be admissible. It can't overestimate. So if we can only move up, down, left, and right, the path we would take from the green start to the red goal, would probably match that path right there. And we could see in both of these cases, the other two heuristics are admissible, right? They underestimate what the actual distance would be, which is what you want. However, if our robot could move on the diagonal, it would likely follow the Chebyshev distance, and we can see the Manhattan distance would actually be overestimated. So it's kind of something you have to keep in mind is, depending on how your robot moves, you may or may not be able to use some heuristics at certain times.
Yeah,
Typically, I think for Micromouse, we use Manhattan distance. Go ahead, Kay. Sorry.
Yeah, the main reason that's actually why I didn't cover Chebyshev distance is because in this competition you can only move 90 degrees because that's what the simulator limits you to.
Right. So the Chebyshev distance, it wouldn't be wrong to use. It would still be okay. It would still satisfy the necessary requirements for the algorithm, but it's not like your closest best fit. Right? You want to kind of estimate. You want to kind of get that estimate to be as close to the actual distance as you can.
In an actual competition, we would be able to use it, but even then, I would say stick to 90-degree turns. Just to, I mean, making 45-degree turns in the competition is a bit more complicated than it might seem. It is a bit easier to run into objects that way. So
You gotta learn to walk before you can. Oh no, you gotta learn to crawl before you can walk.
yeah.
We barely learned to crawl yet. All right, so kind of more of like a higher level, big picture. This is kind of like why we would want to use an algorithm like A star and why this heuristic kind of makes that big of a difference. We could see on the left, that was the original example I had shown with Dijkstra's. And to find that path, it took just under 23 seconds and expanded 18,677 nodes for a total path cost of a little over 50. In contrast, the A-star algorithm took just under 9 seconds to run, expanded 6,000 fewer nodes, and still had the same path cost. So you see kind of a really drastic time increase, or time decrease rather, with A-star. And kind of A-star being a variation on Dijkstra's, there's also variations upon A-star. Some of them kind of notable ones, at least that I came across at Rutgers, was sequential A-star. That's essentially you have kind of multiple searches kind of going on, with each using a different heuristic. And kind of the neat thing about it is you have like one main anchor search, which you need to have the admissible and consistent heuristic for. However, the heuristics you use for your other searches in there don't have to be admissible, I believe. I think it could be inadmissible. I think typically you want to run this when, like, say you had like two parts of the world, maybe not necessarily Micromouse, but maybe you had a robot that was in a field, and then there was kind of like a maze off to the side. Like the heuristic you would want to use in the maze would probably be different than the heuristic you would want to use in an open field. So kind of just comparing those different contexts, different heuristics would be better in certain circumstances. It's kind of getting the best of both worlds. There's also another variation called free directional A star, FDA star, and this is typically when your robot isn't confined to kind of moving in a grid, or can kind of move on diagonal for any real angle. Not necessarily on a 45-degree or 90-degree, but on an arbitrary degree angle. And essentially what this considers is, like before in the example we saw, we only considered the 2 children nodes for each node. Free directional A star will consider any node in like the line of sight. So as long as, if you want to think about maybe like have this like a couple obstacles in this grid or in this maze. So maybe say there'd be an obstacle here. So there would not be a line of sight between A and D. But say that if we remove that obstacle, you could see D from A, and you would be able to consider going from A to D directly rather than through C. I think it's maybe a little bit better explained with diagrams, possibly just that. There's a couple other ones. I think there's B star and D star, and a couple other ones that I probably don't really understand very well, so I'm not really going to get too far into them. But probably the easiest and kind of most straightforward variation on this would be weighted A star, which is essentially, it's the same algorithm as that initial A star we saw. But rather than, if I go back to the algorithm, rather than just taking the cost of the node plus the heuristic, we would take the cost of the node plus some weight times the heuristic. Essentially what that is saying is it's becomes a greedy algorithm. It's because we really kind of put a lot of stock in the heuristic. We say, we think we have a really good heuristic, we want to go with it. And we can see kind of how that weight affects the performance. So having the weight equal to 1, that's just the regular A-star algorithm, right? It's still the cost plus the heuristic. And you see that's the metrics from that one example. But now if we increase to a weight of 2, you see when we go from 8.8 seconds to 1.9 seconds, and we expand 5,000, or expand 6,000 nodes, we expand half the number of nodes, and our path cost only goes up by 3. So you do lose optimality for this, but kind of the processing time is quite you gain quite a lot in that. As you can see, if we kind of drastically increase the weight up to a 5, it takes barely any time at all to run. We don't consider that many nodes, but since we don't consider that many nodes, our path cost ends up going way up. So it's kind of like something you can kind of fine tune, kind of run some experiments with and tweak. It's probably the best way to go about doing it if you wanted to implement it this way. And I guess kind of a comparison to flood fill, which I think you guys are familiar with. I think Kay's gone over it with you. A-star is often referred to as like an offline algorithm, which basically means like the robot isn't moving around and kind of gathering information in real time as the algorithm is running. Right, this is just a calculation. The robot doesn't have to move during all this. It's just trying to figure out, based on what it knows the world around it to look like, what's the best way to get from where it is to some other node. Having said that, that means at the time of running A-star, that requires you to know what the entire world looks like. So in the case of Micromouse, you would have to know what the entire maze layout is, which isn't something you know ahead of time. And because of this, you kind of have to combine A-star with a separate algorithm that will search out the maze for you. And oftentimes, typically when I've implemented this, we just use something like DFS or depth first search. It's kind of a good pairing to have. And on the other hand, flood fill, if you just go with that algorithm, is just the one that does kind of both for you. But since flood fill kind of does both for you, it doesn't know what the maze looks like ahead of time. Flood fill, I don't think, has any optimality guarantees or any properties about that. So, depending on what you may want, if you really want an optimal path, you can go with A-star. If you don't care about an optimal path that much, and you just care about finding the goal, then I think flood fill would probably be the best way to go.
Can I?
And I guess kind of. Oh, go ahead.
Yeah. So actually, no. Wait. I think the next slide covers that. Never mind.
Okay. So, kind of considering A-star in the context of Micromouse, you get a couple of pros and a couple cons. Pros, I would say, would be you have a shortest path. You can. So I guess another thing. I guess I'll leave a second point, but you have the shortest path, so you're not going to be wasting any time kind of running around any loops. You know directly where you're going, and you're going to be getting to the goal. You can also, since it's just a calculation, you can kind of optimize that path that it returns and kind of try to build that path to suit your robot. So I guess an example would be, say your robot, it can't turn on the 45-degree angle and like strafe through a zigzag corridor, right? You can maybe give those cells a higher cost, a higher G value to transition through those. Meanwhile, if you have a straightaway that your robot can really like ramp up the speed through, you can give that a lower cost and kind of tailor the path to best suit the movements of your robot. The negatives for this algorithm is, what I just said before, is you have to know the entire maze ahead of time, which is, that's a big ask. And kind of while searching that, since you have to know where all the walls are, and you have to visit every visitable node, you will have already visited the goal in searching out the entire maze, which is cause for celebration in and of itself. Like if you actually do that in a real Micromouse competition, at least certainly college level, that you'll probably win with that, regardless of how inefficient your path is. And I think kind of the biggest reason against using kind of this combination of a search function, DFS, and A star is as your robot moves through the maze. I'm talking in like a real physical maze with a physical robot. The error accumulates very quickly. So, say you're turning. Typically, you want to think about you're turning 90 degrees in either direction. In actuality, you're turning, 92 degrees, 87 degrees, in either way, clockwise and counterclockwise. And they may not cancel each other out. So if you accumulate, 2 degrees of error at every turn, in 5 turns, you're already 10 degrees off where you think you are. And that goes the same thing with the movement, too. You're not moving 1 cell forward. You're moving 0.8 cells or 1.1 cells. So you have to have a good way of kind of canceling that out and kind of living with that, which is a very difficult thing to do. And
Lot
kind of
harder.
oftentimes that.
Yeah, I'm sorry.
Go ahead.
It's a lot harder than it sounds, guys. I'm seriously not kidding.
Yeah, that's probably the hardest part of the competition is actually just to kind of deal with that error that builds up as you go through the maze. And kind of because of that, it's not very practical to, at least in everything I've seen, everything I've done, is not a very practical expectation to think your robot is going to get through the entire maze, visit every traversable cell, return to the start, and then be able to perfectly travel that optimal path. It's just a bit, I think it's a bit optimistic. I believe that would be the end. That's all I had prepared. If there's anything that you guys want to ask, or if you want me to go over something again, let me know.
Any questions, guys? I have a point I want to make, but I'll say it later if anyone has any questions.
Questions, comments, concerns?
Yes, Stan?
It's good. Not really.
Okay.
Okay. I'm just curious, why is it called A star?
Why is it called A star? I don't know.
Yeah.
Joe, do you
The
know why
star is optimal. I don't know why A. I think that was like the first one or something.
Ah.
Okay.
Wikipedia will tell you.
Okay. Any other questions? Okay. So, Garish, you had something to say?
Not really, but I think there's also something called B star.
Yes. I think that's a little bit of a different application, though. I could be wrong. I'm not really too familiar with the algorithm.
Yeah, I've just heard of something called that. I don't know if it's relevant for our purposes. Oh, I
There's
have a
also D
question.
star. I believe it's dynamic A star. Yeah. What was your question?
Is there any difference in the memory requirements of A star versus flood fill?
That's a good question. I don't know. It would also depend on like your implementation of A star, right? If you're doing the tree search versus graph search.
Right.
I don't know the spatial requirements off the top of my head. I didn't really look into that.
We're using a matrix, so 2-dimensional matrix.
Well, you could do a 2D matrix for that's like your base, graph.
Yeah.
But like while you're running, is what additional memory, I guess.
While we're running, it really depends. I think we keep one stack, and that's after we're coming back from the center.
Yeah, I don't know, because I guess that would compare to the fringe in A star, assuming you're using tree search and not keeping track of the closed list. I'm not sure of like how that would grow and what's the expectations for that.
Yeah, I don't think space efficiency is too much of an issue here. Like, you guys won't run out of memory unless you're
Okay, yeah.
just
That's
adding
basically I was
everything.
asking if it's practical to actually implement on a normal bot.
Oh yeah, it's very practical in that sense.
Okay.
We did
alright.
this my first 2 years, my first two micromouses we did the DFS A star combination.
Is there a reason we moved to flood fill?
It was kind of that last point I brought up was the error accumulation. It's not really practical to um like expect your robot to get through the entire maze. You know, like I said, it's cause for celebration if you get to the middle anyway. Never mind if you took an optimal path. And flood fill is kind of the like A star was kind of like it was like the way to kind of guide Dijkstra's into going towards the goal. Flood fill is kind of like the way to guide your search towards the goal without knowing everything. At least that was my reasoning.
Yeah.
Okay. So for our competition, we don't have to worry about like the accuracy of our turns. So A star would be better than flood fill.
So that's something I was talking to Kay about because you guys have a perfect transition model and a perfect sensor model in your simulation, but apparently they score you on your total amount of turns and your total amount of movements, which which case searching the entire maze would count against you. That being said, I think they only weighted it as like 10% of your score, so I'm not entirely sure which would be better.
Yeah, that's why I said, guys, it really depends on the type of maze we receive as to which algorithm would be better. And that actually is one of the points I wanted to bring up. So, flood fill, you can get lucky on the number of searches you have to actually conduct before you find that, okay, no more flooding is occurring, so therefore we have found our most optimal path. And like Joe said, one search of flood fill is not going to guarantee optimality. You might have to conduct multiple, or you might have to conduct few searches over and over before you find that no flooding is going to occur. A star, you only conduct one search, and then you find the shortest path.
So kind of what I would recommend you guys do is, I know Kay already did his flood fill implementation. Maybe you guys want to do DFS A star combination, and run on the same mazes, see what you guys get, see who scores better. I think you guys will have like what? I think your competition's is it mid-November or late November?
It's on November 21st.
So maybe you guys can kind of before then see if you can get this implemented and just see how it does. Even if you don't get it in time, at least you know for next time.
That's why I'm here. That's why I already have the algorithm ready. So yeah, we were actually talking about this earlier. We could host our own little mini competition to see whose implementation of A star will perform the best. That would be a nice thing to have.
And actually, that simulator is kind of nice to have for this because you can kind of play around with your heuristics, kind of play around with the different weights if you want to do a weighted A star, and see, how that affects your overall score. There's a lot to kind of fine tune with this, so it'd be kind of nice to have a easy way to experiment with it.
So, other than that, there is the topic we still have to pick up on that we discussed last week, and it's gonna be a bit short. I want to see if you guys have thought about it in the meantime, because there was no meeting last week. So, let's see if we can have some more ideas for improving our final score. So let me switch the scenes here real quick. Okay. So yeah, this is what we have so far in our Google Docs. A star, which we just went over today. Prioritizing branches with more available junctions. I think now that we've learned a bit more about A-star, that's kind of what A-star would sort of do, but you'd still leave that up there. And then we have little decision check thing I came up with. Would I exactly call that an estimation? I think
Stopping criterion.
yes. I don't know. Yeah, so this decision type, we, in order to estimate what a potential future score could be, we took R, which is equal to the ratio of turns to moves, which is equal to total turns over total effective distance, and then optimal ratio, which is current turns over current distance. And then we're going to be estimating the best path using that information we just got. So F is going to be equal to estimated best run distance, and that is going to be the flood fill value on the current center cell you just entered. And G, which is equal to estimated best number of unoptimal turns, which is F times R, right? Because total effective distance cancels out. The distances cancel out and you're left with turns. And then H is going to be your estimated best optimal number of turns. And then we find our estimated future scores, estimated total value. What that's going to do is it's going to give you the total score you have, or you think you'll have, after you conduct like 3 round trips around the maze. And then you calculate the estimated future score, which is equal to F, your estimated best run distance, plus H, your estimated optimal number of turns, plus 0.1 times the estimated total value. Right? And we said that this estimated future score has to be at least 10% better than your current score. So it must be less than 0.9 times your current score. All right, so does anyone need any does anyone need a jog? How do I say this properly? Does anyone need any clarifications on this? I was trying to say, does anyone need their memory to be jogged? But whatever. So are you guys good on this idea right here?
It's just the numbers might be like we can test it out with
Yeah.
the 10% and stuff.
Mm-hmm.
Except that
Okay. Did anyone come up with any ideas? Or even if you didn't, can you think of any ideas right now? Potential ways to reduce final score.
I don't know if this is feasible, but there's certain algorithms that they use to generate mazes. So if we can figure out certain biases in those algorithms, we might be able to optimize for the mazes that they'll give us at the competition.
Okay.
Because there's no way that they're making these mazes like by hand.
I don't know about that. The reason why I say that is because some mazes are actually specifically designed for this competition and in order to challenge your robot's movements.
Oof. Okay. All right.
Yeah, I mean, I definitely see
No,
where
just
you're...
the fact that they made 3 in the beginning and then they released 3 more later on, right?
Mm-hmm.
So they're still making new mazes. So I don't know. It didn't seem realistic for them to be making these by hand.
Well, okay, here's the thing. There are plenty of mazes from previous competitions that they could give you for practice, right? And
Oh, okay.
so that's what they could have given us. Right? We don't know. It doesn't matter. But the mazes they typically tend to use in competitions, they're not generated by any sort of algorithm, so to speak. They specifically design the mazes because it's not that complicated to actually like design a like layout for a 256 cell maze. I know there's a lot of like walls to place and all, but it's pretty doable. It's not like
If you
they're
say so.
designing a maze for a 1,000 by 1,000 maze. So
Yeah, I guess so.
but I was actually thinking of that, you know, finding different algorithms to generate our own mazes for practice. I was looking across some that were already present. Main downside to those is that they all generate perfect mazes. Perfect as in every wall connects to every wall in some way. Right? Even if they're not directly connected, they can be indirectly connected. Whereas in Micromouse, that's not the case. Otherwise, the maze would be solvable by a right-hand follower or a left-hand follower. Or yeah, a right wall follower, a left wall follower. There is actually one. I think it's based on cellular automata. If I'm not mistaken, when I was looking it up. The maze generation algorithm. That one's a bit weird, and I'm not really sure as to how I would go about making it generate proper mazes instead of weird mazes, because it is based on the game of life. If you don't know what that is, don't worry about it. But it'll generate some pretty random mazes. let me tell you that. Some of them might not even be valid. So, yeah. Yeah. I mean, the bias idea is nice, but I don't think that might necessarily help us in this competition, unless you want to look at some previous year's competitions and see what the best biases for those would be, and then do something with that. That could work. Okay, so I will just add that actually though. I think this is shared with all of you guys. I did share it last time. If you don't have the... No, wait. No, I put this in the Micromouse folder, right? I don't know if you guys are able to edit it. Are you?
I think we checked last time. I'm not sure actually. I thought we did.
Okay. Okay. Yeah, I made it so that anyone with like a Rutgers account for Google Drive can edit it. Okay. I think I posted the link in Discord as well. So again, if you guys in your spare time want to add more ideas to this, feel free to. I will add what you just said, Girish, to this. Collective bias, right? From different mazes. Okay. Any other ideas? You guys are pretty quiet. Come on, I know you have some ideas. None?
I'm actively thinking.
Okay.
If I ever come up with anything good, I'll let you know.
It doesn't even have to be good. It can be whatever. As long as we have an idea, we can build upon it.
Hear from him tonight.
Girish, are you watching the election?
Half and half.
Understandable. One person actually did ask me if I was going to be recording in case, since he was going to be watching the election with his family. I said that was fine. And I did remember to record this time. I'm checking OBS right now. Yes, I'm recording. So I didn't forget that part.
if you do end up checking anytime soon, you're gonna be in for a very, very, very big surprise.
What?
It's just very unexpected what's happening right now. But
Okay.
Yeah.
Why are you talking like describing it
Wait,
like
what?
it's a TV show?
Apparently, the results are very surprising. I'll view it myself a bit later.
I don't know how election works.
Okay, well,
the thing is about the things that we have written down right now is that, like, when we discussed it last time, right? We implemented a lot of things from like pseudo A star, as in like it's not literally copying the algorithm, but we sort of like proposed things that were related more to like the way it uses like heuristic processes and stuff. So, like today we didn't get that much. At least I feel like there's not much new info to work with.
mm-hmm.
So like, yeah.
Okay. Well, again, this is we still have a couple ideas here. So even if it's just branching off of what it is already there, that's also fine. And it's fine if you guys can't just come up with this already. I know it takes time to come up with new ones that are like effectively different from what we already have, but yeah, just spend some time if you can. You know. And yes, the A-star DFS implementation. All right. So we work on that as well. I think you all have access to the GitHub repository on Rutgers, right?
Yeah.
Okay. I'll set up some different branches that you can all post to, or I might just create. I'll see. Maybe I might create like a subdirectory of some sort. I don't know. I'll figure that out. But yeah, in the meantime, you guys can also, if you can't really, if you're not really thinking of any ideas in regards to this, just work on DFS and A-star because the materials for that are already out there. We discussed it in this meeting as well. You can always reach out to me if you need any help implementing anything as well. And yeah. Okay, Joe, do you have any thoughts on how we could improve our score?
If I did, I would have brought it up by now.
Okay. All right, well, that's it for the meeting then.